Hello and welcome to Cut Saturn Simple Junction tutorial. Today, I'm going to give you a preview of Cut Saturn by analyzing the flow inside the cavity you see on the right. This video tutorial completes a PDF tutorial available in Cut Saturn website. I highly recommend you to download Cut Saturn package, and if you need more information, please check video description. Let's begin this tutorial by creating a top folder in which every tutorial folder will be set. So to do this, I need to open a terminal window by doing this, creating a folder called CFD, changing directory to CFD. Then I will create a Cut Saturn study case. To do that, I need to type the following command: Cut Saturn create space -s. Then you need to type the title of the study case. In our case, it's Simple Junction. Then you need to create a case. You can create as much case as you want, but in this tutorial, only one case will be necessary. So then press return. Once you do that, you created a complete directory including multiple folders. This is how it looks like. You've just created Simple Junction folder including multiple subfolders. The mesh folder in which you need to add the mesh of your study, the post folder for the post treatment, the case folder in which there is also 3 subfolders. So if we take the data folder, you have the setup.xml file, which is very important because it gathers all information Cut Saturn needs to create the CFD simulation. You also have the results folder in which all results will be set, and if you need to add further information for your simulation, you can add sources inside this folder. So now you did this for our tutorial, we need to copy and drag the mesh file, which is located in the examples package, including in Cut Saturn package. So to do that, I need to go to Simple Junction mesh, copy the mesh and paste it in the mesh folder we've just created. So now you have a folder with the mesh file included. Now let's move to Cut Saturn graphic user interface. The proper way is the following way. You need to move into the data folder and then to launch Cut Saturn graphic user interface. Let's do this. So I will change directory and move to the data folder by typing the following command: once you're in, you need to type the following command to launch Cut Saturn graphic user interface. And then if you are in this step, congratulations, you've just launched the Cut Saturn graphic user interface. So now, once this is open, you can clearly see 3 main zones. The first zone is the main window. The second zone on the left is the header tabs. And the third zone is at the top, and it's called the upper icons. You can manage every CFD simulation of CodeSiren with these three zones. So now let's start with the Mesh tab. Make sure your mesh directory is correct. So in order to do that, you can make sure the mesh folder is selected. Just select it and click on choose. Now you can add the mesh you want to. Normally there is only one mesh, the one we just copy and paste. So just select it. It should appear like this. Regarding the execution mode, you just need to leave this standard computation option. So no need to add further information in the pre-processing, neither in the volume zone, but you need to add boundary zones. Regarding our case, we need to add 4 boundary zones. We need to add an inlet. We need to add an outlet. We need to add symmetry. And we also need to add walls. So now we need to specify criteria for each boundary zones. Every boundary zones refer to a mesh side, and all are numbers. So for the inlet, for instance, the inlet is just the number 5. You will add all the information in the tutorial, in the PDF tutorial, if you need to know why the selection criteria is this number. So inlet is number 1, outlet is number 5, symmetry refers to number 8 or 9, wall refers to number 2 or 3 or 4 or 6 or 7. So now you're all done with the boundary zones. Just click here to save your XML file. So now let's move to the Calculation Features tab. You can select the flow models. Here, standard Eulerian single-phase incompressible is a good option. You can now move to the turbulence model by selecting a turbulence model. Here, K epsilon linear production is also a good option. We're gonna activate the energy equation by clicking here in thermal model and selecting temperature Celsius. No need to add body forces and no need to add further species transport. So you're all done with calculation features. Just save your XML. Let's now move to volume conditions. Tick initialization. If you do not, you won't see initialization tab appearing here. So first, we need to fill physical properties. All physical properties values are available in the tutorial. Make sure you follow the values I type here. So density is 7.5735, viscosity 0.5, A3, No need to change thermal conductivity. We need to change initialization values. Velocities, no need to change this, but we'll need to change thermal values. The value to change here, it's 300 down to 20 degrees Celsius. Save the document. And you're all done with the volume conditions. Now let's move to boundary conditions. By default, all nature are wall. You need to specify for each label which nature it is. So for our case, an inlet is an inlet, an outlet is an outlet, symmetry refers to symmetry, and wall is a wall. You can now define for each boundary zones every conditions. So for velocity, select the direction field. You can select specified coordinates and type 1 in X field. Turbulence, just modify the hydraulic diameter to 0.5 and the thermal value should be 300. No need to change outlet value, no need to change symmetry, and no need to change wall values. You're all done with boundary conditions and you can save the case. So now let's move to time settings. In order to do a CFD steady analysis, just select steady local time step, select the Simplug algorithm. You can leave all the values here by default, but you need to change the number of time steps up to 300. You can save the case. You're all done with the time settings. So now let's move to numerical parameters and the equation parameters tab. No need to change the solver values, neither scheme, but you need to change clipping values. The minimal values should be 20 and the maximal value should be 400. You can save the case. Let's move to post-processing tab. The output control and the log frequency should not be changed. You can leave this option. So let's move to writer tab and select results. The frequency should be changed from no periodic output to output every n time steps. You can leave the value to 1. No need to add further information here and no need to add monitoring points too. So you can save the case here. No need to add, no need to change values here neither. So you're all done and you can now proceed to the calculation by clicking Run Computation here. A window just appears and you can set all the processes you need and all the threads per processes you can have. Just before clicking Run Calculation, make sure the advanced options are well ticked or not. In our case, you don't need to tick any option here. You can go back here, leave the values 1 for the number of processes and leave the values 1 for the number of threads per process. You can run the calculation. A window just appears and informs you the status of the calculation. Here the calculation is quite fast. So as you can see, the calculation is finished and you can check it by clicking OK. If the calculation was more time consuming, you could check the residuals by clicking here, or you could either stop the calculation by clicking here. So by now you've just finished a complete calculation, and we could now move to the next step, which is the post-processing phase. Let's now move on to the next phase, the post-processing with PowerView software. As you can see on the window, PowerView software allows users to have a glance on the results. For our case, we can plug the temperature, and we can also check it with this slice, and you can have a glance on the temperature evolution. If you want to, let's say, have the trough temperature at the 10th number 10th iteration, and have it. Please keep in mind that all iterations between first iteration up to steady solution are not physical. It gives you results regarding the simulation. So, for instance, you can change it to 50, and you can see results are evolving. The idea of this, the latest simulation, was to find a solution, a converged solution for a steady solution, and the results are pretty good. You could also add, if you want to, some velocity vectors by adding glyphs. Make sure that no scale array option is selected, and you can decrease scale factor 2. Otherwise you won't be able to see vectors. You can use solid color, and then you will have a glance on the results. So if we proceed by clicking on play, you will see the evolution iteration by iteration of the temperature and the velocity. So these steps concludes this tutorial. I hope you enjoyed it, and if you appreciated it, I advise you to have a look at the next tutorial. Thank you for watching us.